We are finding the speed of sound at 0 degrees Celsius. In order to help with our experiments, we first calculated a reference length and the average room temperature of the area which the experiments were held in. The speed is proportional to the square root of the absolute temperature, giving an increase of about 0.6 meters per second per degree Celsius. We will be using the combined gas law to calculate the room temperature by finding the difference in pressure of an enclosed container after being submerged in ice water. We place the phone inside of the airtight container, let it acclimate, submerge it under ice water, and let it acclimate again. We export the data and look at the pressure difference. The temperature of the ice water is known to be 273.15 Kelvin, as that is the melting point of ice. Plugging values into the combined gas law, we propagate uncertainties, and our final result is 290.4412 Kelvin plus or minus 0.01 Kelvin. We used the inelastic collision experiment in Firefox to calculate the length of a reference string. This experiment looks at the energy loss between each bounce and extrapolates the original height. We drop the ball at the top of the string and write down the recorded value provided by Firefox, which is about 107.76 plus or minus 0.005 centimeters.
So the first idea is using the acoustic stopwatch from Firefox. Basically, two people stand across from each other between a distance of 30 meters. And then we used a string that we have previously measured to calculate the distance between the two people, which is around 30 meters. We used the acoustic stopwatch to measure the time taken for sound waves to travel to the other person and then back to the original person who made a sound. And then once we knew the time and the distance, we used the equation distance divided by time, which equals to velocity, to calculate the speed of sound. Since we have measured the string, the uncertainty for the string would be 0.005. And since we used the string 30 times to get a distance of 30 meters, the uncertainty would be 0.005 times 30, which is 6 centimeters. After that, we also measured the time it took for the sound to travel there and back from person A to person B back to person A. So the uncertainty for the time would be 0.0005.
Another method we will be using includes the Sonar function on the Firefox app. By using the time delay of an echo, we can calculate the speed of sound by controlling the surrounding environment. First off, we opened up the Firefox app and picked the Sonar option, then the speed of sound tab. We put the phone in a container with one open end to constrain the direction of sound. Then, we moved the contraption around 108 centimeters away from a wall using a predetermined length of string. We ran the Sonar setup multiple times and then we recorded the measured values on Firefox, exporting the data for additional analysis. Sonar works by multiplying the time on the x-axis by the speed of sound and dividing the overall result by 2 to give the corresponding distance of the echoes. This formula is manipulated in the speed of sound function, where the distance is already known and the speed is determined by the known values. For a more concrete result, we calculated the average of 5 trials and found the standard error based on the dataset by using the stakes function from Excel, STEYX. In the end, the Sonar method gives us the speed of sound as 346 plus or minus 1.5 meters per second.
Our third idea is to use the frequency of the sound generated by removing a rubber stopper from a wine bottle and the wavelength of the sound wave obtained using the measurement of the wine bottle to determine the speed of sound. To set up, we use one phone to measure the instantaneous sound frequency using the audio spectrum function from Firefox, and another phone to film a person unplugging the cork. Then we look through the video on the second phone to find the exact frame of the peak frequency when cork is unplugged and use that data in the equation. We repeat these steps for different trials and compile the data into a spreadsheet for data analysis. For the calculation, we use the equation V equals lambda times F, where V is the speed of sound, lambda is the wavelength of the sound, and F is the frequency of the sound. The bottle is a closed tube with one end open and the other end closed. When a wave travels through the tube, the closed end has a node while the open end has an antinode. In other words, the length of the tube will only be a quarter of one wavelength. This relationship is condensed into the equation lambda equals 4L, where L is the length of the tube and lambda is the wavelength. In terms of this experiment, L will be the length of the resonator, which is measured from the bottom of the cork to the water level in the bottle, and lambda is the wavelength of the sound from the bottle. We then substitute the equation lambda equals 4L into V equals lambda times F, which gives us V equals 4LF. However, since the acoustic length, the length sound travels, is slightly longer than the tube length, we need to account for the correction. The formula of the length correction is delta L equals 0.61 times R, where delta L is the length correction and R is the radius of the bottle. Finally, we combine all of the equations. The audio spectrum displays the frequency in Hertz from the bottle when unplugged, which will be the frequency we will use in equations. The tube length, which is measured from the bottom of the cork to the water level in the bottle, is measured using the string from the previous length measurement. The diameter of the bottle is also measured using the string by folding it in halves.
The uncertainty for these measurements was based off the most confident visual estimation of the folded string. The measured frequency is very consistent and the value was always at 1218.75 Hz. Plugging the values into the equation and propagating the errors yield 366.70 plus or minus 13.85 meters per second. Lastly, we use the relationship between air temperature and the speed of sound to calculate the final value. After substituting the numbers and calculating the errors, we get a final value of 356.32 plus or minus 13.56 meters per second. This method uses the Doppler effect to calculate the speed of sound. The Doppler effect is the compression of sound waves caused by the relative motion between the observer and emitter. The compression of sound waves will change the perceived frequency of the observer compared to the resting frequency from the emitter. For this case, we modify the Doppler equation to find the relationship between the change in perceived frequency and the acceleration of a moving observer. We did this because we can accurately determine the acceleration of the observer using the accelerometer function, and we can find the rate of change in perceived frequency using the Doppler effect experiment in Firefox. F is the observed frequency, F naught is the actual resting frequency, V is the speed of sound in air, VO is the speed of the observer, Vs is the speed of the source. The speed of the source is 0 as it remains stationary during the experiment. Next, we take the derivative with respect to time for both sides, where V, O, and F are the changing variables. After implicitly differentiating, separate and isolate V. Notice that dV over dt is the acceleration of the observer, hence we rewrite the equation as speed of sound equals resting frequency times the acceleration of the observer divided by the rate of change for perceived frequency. Materials: 2 phones, a flat plank of wood, some elevated surface. Angle the plank so it forms an incline. 1 phone will be the emitter, which stays stationary, and 1 phone will be the moving observer. Slide phone down the ramp. Calculate acceleration down the ramp using the linear accelerometer. To calculate the change in frequency, we'll repeat the process but with the Doppler effect experiment on Firefox. Ensure the surrounding environment is as quiet as possible to prevent faulty data. After exporting all the data to a spreadsheet software, we clean up the data and remove any obvious outliers. For acceleration, the start time and end time are demonstrated with 2 visible spikes in the recorded values. We find the average acceleration for the linear acceleration trials, and we also calculate the standard deviation. For the Doppler effect data, we ignore everything except for the time and frequency. The data range is the section with an increasing frequency because we know that the observer is moving towards the receiver. We do the same thing and remove outliers and clean up the data. The change in frequency is then calculated using the linear regression function. We then calculate the standard error using STEYX, average all trials and errors, and plug the values into the derived equation. We propagate the uncertainty by adding the percentages uncertainties, and the final value is 341 Next, we average all trials and errors and then plug in the values into the derived equation. We propagate the uncertainties by adding each of the individual percentage uncertainties. The calculated value is 340.83 plus or minus 6.77 meters per second. Lastly, we calculate the room temperature using the method outlined at the beginning, and we plug in the speed and the temperature into the equation relating the speed of sound and air temperature to find the speed of sound at 0 degrees. By propagating the uncertainties and calculating, our final value is 330.5 plus or minus 6.8 meters per second.